Hi, I want to thank you for tuning into this session on enabling edge computing in LTE networks. The title of our paper is P4EC, Enabling Terabit Edge Computing in Enterprise 4G LTE. I'm Max Hollingsworth from the University of Colorado, and I'm pleased to be presenting on behalf of all of the authors you see here. The first thing I'd like to do today is highlight a few big changes that are happening right now in 4G LTE. Currently, there are only a handful of mobile network operators operating in the United States. These are the ones you're thinking of: Verizon, AT&T, T-Mobile. But the number of mobile network operators is likely to grow rapidly due to recent changes in spectrum policy, which are encouraging many small-scale network operators to join in. It all started in 2012 when the FCC allocated 150 megahertz of spectrum in the 3.5 gigahertz band for use by private LTE operators. This is called the Citizens Broadband Radio Service, or CBRS. It took a little while, but things are finally starting to take off because in September of 2019, the FCC approved the first commercial deployments of the CBRS system. When coupled with license-assisted access operating in the 5 gigahertz band, there's quite a bit of spectrum available for use by small-scale network operators. CBRS and LAA are seen as particularly applicable to enterprise, campus, and municipality scale LTE deployments. These enterprise deployments will, however, have a different underlying network structure than what's previously been used in larger deployments. To understand this, let's quickly look at the structure of large deployments. LTE networks have three major components: the mobile device, called the UE, or user equipment, the radio access network composed of base stations, also known as E-Node Bs, and the core network, known as the EPC. The EPC serves a variety of functions, including subscriber authorization, managing UE movement, and provides a packet gateway, or PGW, to the internet. A large mobile network operator, such as AT&T, typically uses one EPC to serve a very large physical region, sometimes many states. All cellular traffic in that region passes through the PGW on its way to the internet. With this increase in the number of small-scale LTE operators comes an opportunity for cloud providers like Amazon to offer a cloud EPC. A cloud EPC model would mean the network operator purchases physical E-Node Bs, similar in size to a Wi-Fi router, and deploys them over some area, for example, a warehouse or a campus. All this with an internet backhaul to connect to the cloud EPC service. The cloud EPC simplifies the deployment for the enterprise LTE operator, but it also binds them to the latency created by having a packet gateway in a distant cloud data center. Why is this a problem? Well, there are many latency-sensitive applications that rely on LTE, for example, augmented reality, wearable cognitive assistance, and IoT sensors. Latency can be very crucial in public safety applications. For example, command and control applications used by fire departments. These are a good example of a localized, time-sensitive service that cannot rely on a distant cloud data center. These applications provide firefighters with critical information such as orders, location, and movement. If firefighters arrive at a fire and wish to piggyback off the coverage provided by one of these enterprise LTE networks, well, the network wouldn't be able to provide public safety members with the low latency services simply because of the distance of the cloud EPC. Our solution to the latency issues caused by the cloud EPC is the P4EC. When deployed, the P4EC acts as a middle box monitoring all the traffic between the E-Node B and the EPC. Using custom P4 programs, traffic deemed latency sensitive can avoid a trip to the cloud EPC and is redirected to the local exit. This way, the UE has access to low latency services, such as accessing nearby mobile devices, fog services, or localized information. So in general, the P4EC serves two roles in an LTE deployment. First, it provides quick access to edge computing resources physically near the E-Node B, thus offering faster round-trip communication than the cloud. And second, the P4EC acts as a bump in the wire for non-fog-bound traffic. P4EC, which stands for P4 Edge Computing, is a programmable P4 switch using the Barefoot Tofino chipset with multiple 100 gigabit Ethernet ports. The Tofino switch provides line rate packet processing with an aggregate 2 terabits per second throughput. At this throughput, the P4EC switch can easily handle the combined traffic from over 7,000 eNode Bs. Each eNode B, in turn, can handle hundreds of active UEs. The switch itself costs slightly more than $9,000, making the price per active UE roughly a penny. We tested the P4EC in our fully functioning LTE network. This diagram shows the 4 LTE entities, the eNode, the UE, the eNode B, the P4EC, and the EPC. The UEs are a Galaxy S8 and a Motorola Moto. All testing was performed in a Faraday cage. The eNode B is a Juni LTE small cell and is physically located in our lab. When powered on, it establishes a connection with the cloud EPC. We use the open source Next EPC deployed on the Google Cloud Platform. The P4EC runs on a Stortus P4 switch located in a server rack in our lab. Before we dive into more implementation details, let's look at some results. We first used web browsing as a simple but real-world application to test with. On the UE, we run curl to repeatedly measure the total time to download a web page. The download size is 100 kilobytes, and the UE and server exchange about 150 TCP packets. The web page is hosted geographically near our facilities and was specifically chosen to show off the advantage of having a local exit near the eNode B. The figure on the left shows that the median latency fell nearly 300 milliseconds and the variance greatly narrows. Although not shown here, by using the local exit, we avoid a 26 millisecond travel time to the cloud EPC and back. But 26 milliseconds falls short of explaining the 300 milliseconds of savings. The cause is likely the compounding effects of buffering at routers and other middle boxes in the internet, along with waiting for TCP ACKs to travel the extra 26 milliseconds. Next, we evaluated P4EC's performance with live video streaming. The video calls were established between a Galaxy S8 and a laptop. For the evaluation, we measured the end-to-end streaming delay, which is shown here. End-to-end streaming delay is the lag time from when the video frame is generated at the sender until it is displayed at the receiver screen. Thus, it consists of video capturing, encoding, transmission, decoding, and rendering delays. The local exit causes a large reduction in delay, more than 100 milliseconds. Video streaming is a good analog for applications that benefit from a local exit, like the command and control video streaming used by public safety members that we talked about earlier. Here we explicitly show the advantage that the local exit has over the nearest data center and other data centers that are increasingly far away. The results you saw before were all testing the local exit against the closest possible cloud gateway. But in practice, the cloud EPC may be hosted in a less than ideal cloud region like Virginia or Belgium, seen here. In those situations, the value of the P4EC local exit becomes amplified, and it also offers some flexibility to the network operator who can now decide to deploy the cloud EPC in a suboptimal location for cost or convenience, etc. Alright, let's dig into some of the implementation and design decisions needed to create P4EC. To identify the authorized UE, we monitor the S1 control messages that pass between the eNode B and the EPC. When the P4EC sees an attached request message coming from the UE, it looks for the UE's identifier. Highlighted here is the UE's temporary mobile subscriber identity, or TMSI. Then we monitor for the response coming from the EPC, which contains the tunnel ID and the IP address it assigned to the UE. P4EC adds the tunnel ID and IP to its matching tables and uses them to identify and monitor the data traffic coming from the UE during the rest of its connection. For now, we assume that the network operator knows the IMSI or TIMSI of the authorized UEs. As part of future work, we'd like to have the UE transmit packets to the P4EC to self-identify as an authorized user. The next design decision is which packets to reroute. Not all of the authorized UE's traffic is redirected to the edge. To identify which content is deemed latency sensitive and should be redirected, we use transport layer redirection. This means that P4EC examines a packet's IP addresses, ports, and protocol, often called the 5-tuple. When a packet's 5-tuple matches, the destination MAC address is changed and it's forwarded out the port towards the edge, where a surrogate endpoint, which is labeled NAT here, is waiting. The NAT has a knowledge of the edge network's topology and load, then forwards the packets on towards its destination. Network address translation also happens here. Note that all of the NAT's duties can be performed in the P4 switch at line rate. Finally, the P4EC switch must encapsulate and decapsulate packets that use the local exit. This is because all data is tunneled using the GTP protocol between the eNode B and the EPC. When a packet is rerouted to an edge server, the decapsulation action removes the outer IP, the outer UDP, and GTP headers. The P4EC modifies the outgoing MAC and optionally the source address if performing network address translation. For a return packet from the edge to the UE, the P4EC must inject the packet back into a GTP tunnel. The packet is encapsulated with the appropriate IP, UDP, and GTP headers and is sent to the eNode B. These headers mimic the packets coming from the EPC, and the GTP tunnel identifiers are tracked by monitoring the S1AP packets. And that's it, so thank you for joining in. And thanks to my co-authors, Jinsung, Zhang, Jihoon, Sangtae, and Dirk for all the help making this possible. And here are our emails if you have any follow-up questions. Goodbye.